Hello everyone, this is Dr. Zach, and today we are going to learn about LHopital's rule. LHopital's rule is used to make the indeterminate forms of limits a lot easier to solve. So let's get started. While working on your lesson preview, you recognized that when you substituted your -1 into your function, that you had a 0 over 0 form of your equation, which is an indeterminate form of a limit. When you used factoring to simplify your problem, you saw that your factors canceled out and you had a removable discontinuity at -1. Now this removable discontinuity, we are going to exploit and figure out ways to find the limit in a whole lot easier fashion. The second question had infinity over infinity when you substituted, and you ended up with a 3 over 2 when you found your horizontal asymptote heading towards infinity. Now the third question took a little bit more work. You had to do your factoring, rewrote the problems, your limit as x goes to 0, your e to the x minus 1 times e to the x plus 1 over e to the x minus 1. After factoring, you were able to substitute and came up with 2 as your limit. Now these problems weren't too tough to figure out, but it would be better if we had a different way. Question B is a reminder of how to find inverses again, just to make certain you understood that from the last lesson. So indeterminate forms of the limit come in the form when you substitute 0 over 0 or infinity over infinity. These are indeterminate because they do not guarantee that a limit will exist. Now, we're going to apply something called LHopital's rule. LHopital's rule can only be used if your limit is in the indeterminate form. That would either be 0 divided by 0, infinity divided by infinity. Of course, it doesn't matter if it's positive or negative, as long as you get some sort of indeterminate form. Now, as you look at example 1, really what we're trying to figure out is which is faster. Is the log of x to the 5th faster, or is x faster? When you substitute, and you really should, you end up with infinity over infinity. Which infinity is faster? So the way LHopital's rule works is if you have an indeterminate form, you can look at the derivatives of both the numerator and the denominator to determine the limit. So we did take the limit as x goes to infinity. Let's do algebra first, as always. We have 5 log x over x. Now we're going to find the derivative of both the numerator and the denominator. So not to be confused, of course, with the quotient rule. You end up with 5 over x divided by 1, which as you go to infinity is 0. So the limit of this complex function has just now been simplified to become 0. So as a limit review, you should always try substitution first. If you have a 0 over 0 form, you have many different ways you could figure out your limit, but now we can add LHopital's rule. If you have a number over 0 form, there's a vertical asymptote, no LHopital's rule. You have some special trig rules. Now look at your special trig rules. If you apply LHopital's rule, look at this. Don't you get the answers you expected? Now, when we're playing with tail-end behavior, still no LHopital's rule, and their limit, of course, does not always exist, but the left side must equal the right side for the limit to exist. So let's look at example 2. When I substitute, I get e to the negative infinity times the square root of infinity. Now that is neither 0 over 0 or infinity over infinity, unless we do a little bit of algebra. You know I love my algebra. So when we rewrite this problem, let's write it as the square root of x over e to the x. Now when I substitute, it's in the form of infinity over infinity, and I can apply LHopital's rule. And LHopital's rule allows me to find the derivative of the numerator and the derivative of your denominator and resubstitute. So when I substitute infinity now, I get the limit as your x goes to infinity. You know what? Let's write this as 1 over 2 x to the 1/2 e to the x. And look at that. It's 1 over infinity or 0. So L'Hopital's rule made that complex problem a whole lot easier again. Okay, so now this problem. When I substitute infinity in, I get 1 plus 0 raised to the infinity power. So that is not in the form of L'Hopital's rule, because 1 to the infinity power is not 0 over 0 or infinity over infinity. But we are clever people. Let's set this equal to y. And whenever you have variables to exponents that are variables, you know that we should log both sides. So if I rewrite my problem, I have x natural log. Here's my limit as x goes to infinity, 1 plus 1 over x, and that's going to equal the natural log of y. So if I then look at the right-hand side and try substitution again, let's pull that limit as x goes to infinity outside, and I have x times the natural log 1 plus 1 over x. When I substitute, I get infinity times log of 1, which is 0. So again, not in the indeterminate form. We're going to be super clever though. Rewrite the problem. Limit as x goes to infinity, 1 over x times the natural log of 1 plus 1 over x. So now when I substitute 1 over 0, because that's what we get, this term is going to 0, and this is also 0. 0 over 0 is the indeterminate form, and now I can apply L'Hopital's rule. And once I do, the derivative of the natural log of 1 plus 1 over x is 1 over 1 plus 1 over x times negative 1 over x squared, divided by the derivative of 1 over x is negative 1 over x squared. Conveniently, the negative 1 over x squareds cancel out, and this is the limit as x goes to infinity, 1 over 1 plus 1 over x, and we all know that that is 1. However, we've lost track of the right-hand side of the equation. This was equal to the natural log of y all the way through. So now let's solve for y. Y equals e to the 1. So that tells us that this limit, no surprise, is equal to e to the first power. And that would be using L'Hopital's rule and finding derivatives. So I have 4 questions that I want you to practice. Once you've practiced, double check your answers to see that you are getting the same answers that you would expect. Today's lesson follow-up is on page 564. Look at the multiples of 3 and then, of course, questions 43 through 50. You have a fabulous day.